welcome back. Just as a very brief reminder of what we did yesterday. So, in some sense, the main thing we have seen, apart from a kind of a trivial case of a measurement, is an argument by Wigner. And this is an example, maybe one of the first arguments that in some way you can regard as an argument that constrains or limits the space of possible interpretations of quantum theory. So it tells you if your interpretation of quantum theory has a certain properties, then you may run into problems. Maybe to be a bit more precise, this is again just a summary. So, so Wigner's argument, you remember maybe that we made this explicit that there were assumptions to the argument. And one of the assumptions was, I call it here as assumption 1, or I called it assumption 1 also yesterday, is in some way there is a unique wave function that we can assign essentially to the universe in some way, if you like, or to at least a big experiment. So I don't want to describe it here in detail, but just as to remind you, unique wave function. So it's in some way analogous to the way we think usually about, let's say, the electromagnetic field. We can assign to any point in space, time, a field strength. Of course, the coordinates of that or the components of the vector may depend on the coordinate system, but we would agree on where this vector points or what tensor it is if you're thinking of tensors and so on. So there is something kind of objective about the wave function. And this is sometimes called the ontic view. So there's an ontic understanding of the wave function reflected by this assumption. Then assumption 2 was more about how we connect measurement outcomes that we observe to the wave function. And in some way one could say, I didn't write it like that, but let me now write it like that. If an agent A observes something, like for example he observes a certain outcome, the value set is something. Let me write blah. Blah is just a placeholder for something he observed. Then the state of A. So now we also regard, remember in Wigner's argument, you also regard agents, or in this case the friend, as physical systems, so they have a state. Then the state of A is a corresponding state which would reflect this fact that he has observed that. So that would be kind of the state of the agent A. So in the particular case of Wigner's argument, I wrote here an F for this particular agent, but this would be the general assumption that if someone observes particular value, let's say z equals 0, then he's in the state z equal to 0. Now there was a third assumption which I didn't write down as an assumption, but this was kind of our, let's say almost, maybe I should call it the zeroth assumption, kind of the basis of everything, which is that the quantum formalism is valid in some so, and maybe I write it like that. Quantum theory is universally valid. This is kind of the assumption that Wigner tried to falsify, as that he assumed that by contradiction. And then what Wigner's thought experiment shows is that these three assumptions are contradictory. So if you analyze the thought experiment that I wrote down or described yesterday, then 1, 2, and 0 together imply contradiction. I write this arrow here for a contradiction. So Wigner, he took a less neutral position. He said, this shows that 0 is wrong. Quantum theory cannot be universally valid. There must be a collapse of the wave function if an agent is involved. But of course, you can formulate it in this more neutral way and just say one of these assumptions was wrong. It doesn't have to be 0. Maybe you want to hold on 0 or stick with 0, and then it may tell you that it's wrong to think of the wave function as something that is universal and unique. And this is, by the way, for example, what so-called epistemic interpretations do. I mentioned that also yesterday. For example, cubism or the relational quantum mechanics as proposed by Rovelli, also modern form of Copenhagen. They give up this first assumption, then you're again fine, because you only reach a contradiction if you assume all of them. Then another set of interpretations, for example, Bohmian mechanics or many worlds, and I didn't explain them in detail, or actually I didn't explain them at all, but just to tell you there are interpretations like Bohmian mechanics that deny two. So for example, in Bohmian mechanics you would say this observer can still, according to quantum mechanics, be in a superposition, but we have this additional variable, the hidden variable that tells us what the outcome is, and only this hidden variable has to agree with the actual observation, not the state. And then you're again fine. And this is, by the way, true, I would say, for all modern interpretations, because Wigner's argument is a very old argument, and clearly if someone developed an interpretation, he rather be compatible with this Wigner's friend argument to make sure that he's not immediately running into a contradiction with his interpretation. So, in other words, this is a first test. If you have your own interpretation of quantum theory, you can always run it against this argument and check, is at least one of these assumptions violated? If not, then you have a serious problem with your interpretation. Yes?
So just to make this clear, 2 really means, because A is just a subsystem, that the state will be a product of Z equal blah times the rest of the unit?
Yes, it kind of implies that, because as soon as it's not a product, then it will be a mixed state on this system if you trace out the rest. Yes. So this is a pretty strong assumption in that sense. So it's not in some way a big step to give up this assumption here. This is something, it's a really strong assumption in some way to require that the state is now that. But it makes sense if you really think of the quantum state as an ontic state, as this is reality. Then you would say, if I've seen Z equal plus 1/2, then it should really mean I'm in the state Z equal plus 1/2. But admittedly, it's probably not a very good assumption, and we will no longer consider that in what follows. Yes?
What does it zero mean? Because if we think as of these 3 subsystems, subsystem of the whole universe,
yes,
then the evolution of reduced density matches is not unitary, and everything will change.
Aha. Yes. So here I said quantum theory is universally valid, and I wasn't very precise about what quantum theory means. So in some way, what you needed for the particular argument that Wigner made is that if you have an isolated system, then the state of that system evolves unitarily. Of course, this implies that if you now look at the subsystem, there is a particular evolution which may not be unitary. That's all fine. So I think I could have been more precise and just say we assume isolated systems evolve unitarily, and in addition we assume the validity of the Born rule.
But why cannot we just say that this subsystem is not isolated then?
To say the system is not isolated. Yes. So by construct, okay, this is a good point. So in this thought experiment, maybe you remember I had drawn this box, and there was the friend F inside the box, and we said this box is isolated. So we just so by construction of this thought experiment, it's an isolated system. Now you may of course argue and say, maybe in reality there is no such isolated system. And that's why I made this comment about thought experiments. So physics, so there is no physical law that forbids to have such an isolated system, even though it's extremely hard to build it.
But if we
yes, sure.
use this experiment of isolated system, then in our conclusions we use like our consciousness and how human behaves. So we use the fact that when the human measures the experiment, he kind of knows the result. But because we've never been in an isolated system, maybe that's why. So we don't know how it will be in the isolated system.
Aha. So okay. So if I understand correctly, you're asking if we were, let's suppose this room was now perfectly isolated, at least for a moment. Let's say for the next minute we are perfectly isolated. Now we do an experiment here. Would I still see an outcome?
Yes.
That's what you're doubting.
Yes.
Okay. So I guess yes, we will still see an outcome, because this isolation could be far away. So let's say if this isolation is 1 minute away in speed of light, then I couldn't potentially even notice that I'm isolated. But this is indeed, at the end, it's an assumption, and this is in some way assumption 2. Of course, you could deny that. You could say, let's suppose I'm doing an experiment, and I'm doing this experiment perfectly, in a perfectly isolated environment, then I don't see an outcome. That's Sure, yes, yes.
I mean, if we are in an isolated system, what I want to say is maybe human behaves like a machine. So if you have measurement instrument,
Mhm.
then you don't have this problem, right? The problem
Uh-huh.
comes only if you have
Okay, this.
we don't know, we cannot
Yes.
know how
Okay.
to treat human in isolation.
Yes. Okay. So maybe you have seen yesterday I've talked about, I mean, Wigner talked about consciousness and so on. I don't like this talking about consciousness and human because it's very vague. So maybe can defer your worry to the end of, let's say, this today's lecture, because I will actually now provide a different argument which is not based on anything like consciousness, and where it's actually sufficient to think of agents as a machine, which probably would then resolve your worry, because then it's quite clean what you mean. Because indeed consciousness is something we cannot capture. But even if I write down this argument like that, then there is no consciousness appearing. It's just this second assumption which you can say is motivated. So if someone asks, why do you believe in this second assumption, then you could say, we know because we are conscious beings, we know we actually observe such things. So maybe no one ever observes something, and then this assumption too would be contentless.
So we're going to ignore the problem of consciousness.
So now we are going to kind of ignore it in some way. So Wigner clearly, I mean, his paper even had the title, had in the title something like consciousness. So he clearly saw that as a main ingredient to his argument. But I would say we could really replace this consciousness by this assumption 2, and then we don't need to talk about it. Now I would like to no longer talk about consciousness, because I don't have any idea what consciousness really is, although I feel I'm kind of conscious now, but I still don't know what it is. So I'm trying to go back to the, let's say, physics things that we understand better than consciousness.
But just your agent, your observer,
Yes.
is part of the system, part of this isolated system?
Yes, is part of the isolated
And
system, yes. That was part of Wigner's argument.
And does the observer, when you call it an observer, do you imply that it's a classical...
No,
lies
no.
outside the realm of quantum?
No, this is not. So this was kind of, so the, let's say, crucial ingredient of Wigner's argument is to say that of course he at the end wanted to argue that observers, humans, are at the end not described by quantum mechanics. But in order to run the argument, he assumed by contradiction, so to speak, he assumed, let's suppose even an observer is just a quantum system. And this was then assumption 0, because if you assume quantum theory is universally valid, then in particular it's also valid to describe a human. And so he assumed that, but he wanted to show it's actually wrong. And because he arrived at the contradiction, and because he believed so firmly in 1 and 2, he indeed concluded that an observer as a human is not described by quantum theory. So this was a conclusion, not an assumption of his argument. Okay, now I move on. This was just a review of what we did yesterday. And today I would like to present another argument which is in some way has a similar goal. Like Wigner's argument, it wants to constrain or limit the space of possible interpretation. So again, after I presented this argument, you can take any interpretation you like, check what it does, whether it satisfies the assumption, and then kind of reflect for yourself whether you now think this is a good or bad interpretation. And maybe I should say, at least in my opinion, all currently known interpretations run into serious problems if you apply them to this argument. But I leave it to you at the end to judge whether this is indeed the case. So that's the goal. So it's an extension of this argument. Now, as a kind of so what is it based on, this extension of the argument? There is one main idea behind it. And if you understand this idea, you can already see why one can kind of derive arguments. And I write this down in the following sense. It's kind of an idea which is very similar to what I just answered before, that if quantum theory is universally valid, we can apply it to an observer. Now, the idea is the following. If quantum theory is universally valid, then I should in particular be able to apply it to a physical system, which I could call an agent, that itself applies quantum theory. So it's kind of a recursive use. I use quantum theory to another, let's call it an agent, who uses quantum theory and check whether this description is consistent. So now if I talk about an agent, you can for the moment really think of an agent as a computer. So maybe I write this here as a picture. So and this makes maybe things clear. So there's no consciousness and so on. So an agent is for me in the following something like this. You have, so I will still draw an agent as a human, but the idea is that this is really, you technically can think of this, if you like, as a computer. So what does this computer do? The computer gets as input, let's say, a measurement outcome. So he gets access to a measurement outcome, which is given to it as a physical system. Again, so that's clear what we mean. I mean, you can think of it, you have a memory cell in which or a notebook on which the outcome is written, which is itself a physical system. You give that to the agent, and what the agent produces is an output. And the output is in some way a conclusion that can be drawn using quantum theory. So it could make a conclusion, which I will later think of it like there's a notebook and it writes the conclusion on this notebook. So it's kind of a machine that takes as input measurement outcomes and writes, really, maybe you can think of it as like in plain text, a conclusion. I will just make some examples, but very simple example would be that as input, it's, let's say, okay, maybe I should first say that so you could really think of this as an algorithm which is programmed to do that. So you program into a computer how one should use quantum theory. You also program into the computer maybe a description of the overall experiment that you're going to do. For example, you could program into your computer that you have set up a Bell experiment, that the initial state will be an entangled state, let's say between two sides. And now you could give in as an input to the program, on one side you measured spin up. And then you expect this computer to make a prediction of what will be the outcome at the other side if you measure in a certain basis. So that's really a machine that just uses quantum theory. And so,
but the outcome is going to be quantum.
Yeah, so now, okay, this is now a machine. It's itself a physical system. So the point will be that everything, all the elements here, the input system, you could also think of the input as a notebook which has written on it, this and this outcome was that, is a physical system, which I could also describe again using quantum theory. This is an information processing system, a computer, which I can again describe using quantum theory. The notebook is something where I write down the conclusion, which I can again see as a physical system. So the point will be of the idea that I can now think of another agent. Maybe. Yes, so this is a good point. So in general, I wouldn't like to restrict that. However, it makes it much easier if you only think of deterministic ones. So I will only need the case where all conclusions are deterministic, which makes it much, because then I don't need to interpret probabilities and so on. So this is actually a key point of the argument, that we don't need to already have an a priori interpretation of probability, except if you want probability 1, which we consider as deterministic predictions. So the predictions will always be of the type, I mean, let's say this agent writes something of the form, I'm now certain that this particular outcome will be z plus 1/2. This is the type of thing. It will never be a probabilistic one in this argument. Of course, in general, one may allow that, but this would be harder to formalize, and I wouldn't know. I mean, I would need to make additional assumptions, and so I'm happy I can.
Not me, because I'm never sure about anything.
Okay, yes, so that's a good point. One can never be sure about things. Let's come back to that, because that's an important thing. I will maybe already now say that the argument will kind of be robust. So you can replace all be certain by I'm almost certain, and as long as this almost is sufficiently true, then everything still works. So in that sense, it's fine. There was another question, I think, somewhere. No? Okay. So what is this idea? So the idea is that someone could now, because these are now all well-defined physical systems, someone can say this is again a physical system and apply quantum theory to the description of all that. That's the main idea. So maybe I write, because this is really, I think, an important idea that has, in some way, is an idea that is not new, but I haven't seen it much in treatments of quantum theory. But it's quite obvious that any physical theory that you have, whatever it is, if it's supposed to be universally valid, then it should in particular be able to describe physicists who actually apply the theory. That's kind of makes probably sense. So, so the idea is, if a physical theory, I just write it in words because I really think this is something you should remember. If a physical theory T is universally valid, and by universally, actually, it doesn't need to be now valid on any scale, like on the scale of galaxies. It's sufficient that it's valid on the scale where we operate. So you can replace this universally by, let's say, on all scales that are relevant for our own operation, so to speak. Then T, this theory can be used to describe or to model or to analyze, or if you like, an agent. And an agent should now be understood in this sense here, who uses T. Okay, that's really the basic idea. And we can do that, and of course we want this to work, otherwise we are in trouble. And if this is not true, then I'd say that probably this theory has some major internal inconsistency or so. Okay. Now, I didn't say, okay, when I wasn't here yet very specific, I said this is a computer that applies certain rules to compute predictions or to draw conclusions. So now I want to be more specific and say, what are these rules? And essentially I will assume, and again, you should just think of, you now go there and program a computer with these rules that I'm describing. And one rule I will call Q. And I will describe it informally, but of course it would be a bit painful to write down an algorithm. But the idea is that what I write down here informally can actually be made very precise and turned into an algorithm. Of course that would require some work, but it should be sufficiently precise to do that. And we will actually then in the example kind of impersonate these agents and run this algorithm, so to speak. So it should at least what I write down be sufficiently precise that we know what to do in the concrete case that we are going to consider. So here, let's just say, let S be any system S, and I call here this word around agent A. So with that, this word around should just exclude the possibility that an agent describes itself. Of course, that I may allow that, but that I don't know how to treat in quantum theory. So I don't know how in quantum theory I can apply quantum theory to myself. I know how to apply it to someone else, but then I get into a kind of strange loop if I apply it to myself. So I'm not claiming this is not possible. I just don't want to talk about it again because I wouldn't know how to do that. So let's be on the safe side and just consider systems which are outside of an agent. I'm not trying to describe myself if I'm an agent. So in other words, the computer here doesn't try to describe itself. Now, if A knows, and knows you can now think as it was programmed into the computer that this is the case, that the state, or it has derived it. I mean, either it was directly programmed or it has derived it by applying a unitary, and so the usual laws, which I will now not make explicit, but I guess you know what the usual laws of quantum theory is. It's just a unitary evolution. Let's suppose it has derived that the state is phi s, and there will not be any ambiguity here in the examples. We will all agree what this state is. That will just be essentially given by the description of the thought experiment. And that this system S, sorry, this was now not the proper sentence, that the state of S is phi S, and that S is measured in a basis, and I'll just select any basis. Let's suppose it's an orthonormal one, but it's not actually even necessary to assume that. But let's label the basis element with numbers, and I consider it only finite ones. If you like, you can have infinite ones, but this will not be needed for the thought experiment. And that phi S has overlap 1 for some k. So with one basis vector I have overlap k. This is now exactly the deterministic case that I mentioned. So if in the special case where we are determinist, where I mean, what would you do if you are now an agent? What would be your prediction? If you know the system is in this state phi, this state phi has a perfect overlap with one of the basis states. What can you say about the outcome? I mean, that's probably, it's k, yes. Then, and now let me write it like that, then A, because I think this picture of having a notebook is really useful in this context. A writes into her notebook this is just what she writes. We don't question whether it's true or not, it's just this is what she writes into her notebook. She writes, I'm certain that the outcome is K. That's what she would write. This is what an agent does. So this is now essentially the definition of an agent. It's a computer that applies that rule. Whenever this happens, whenever the input and the program is such that this condition is satisfied, she outputs that onto her notebook. That makes sense. That's kind of a quantum mechanical agent. As I said, this is not extremely precise, but it's clear that you can make this precise. I mean, it's essentially really programming quantum theory into a computer. Now there will be a second rule, and this rule I call C. This is again a rule that I program into it. You can later ask whether it's a sensible rule or not, but it's just something I could program into a computer. And this is now motivated by the following fact. So we will, of course, like in Wigner's experiment, have a multi-agent scenario. And there are physical theories which are kind of what people call solipsistic, or interpretations, where if you are an agent in this theory, you consider everyone else not being an agent, and you don't care what they do and so on. So these are usually not, okay, this is something that will not match with this. So I'm kind of, now I want to have an additional rule where these agents kind of acknowledge that the other agents are also agents in that sense, which makes sense because we defined them as programs. Now, because all agents apply the same rule, I'm essentially in the following situation. Suppose that, there are here all people who know quantum mechanics very well, and let's suppose we discuss and we agreed that we have the same understanding of quantum theory. Let's say I had discussed that with John, and now John has really the same, or maybe I probably learned actually quantum theory from you by reading your script. So in that sense, I have the same understanding of quantum theory as you have, if you still have the same that you had when you wrote your script, which I assume. Now, let's suppose you do a calculation. Now you said you're never certain about the outcome. Let's suppose that you did a calculation, wrote down into your notebook that you're certain, or almost certain if you like, that this particular outcome will be that. Let's say you concluded from your calculation that will be a dessert served tonight. Now, suppose I do this analysis and consider you as a system, but I come to the conclusion that what you will write into your notebook is indeed that there will be a dessert served tonight, that you are certain there will be a dessert served tonight. Now, the idea is that because I know you applied the same theory as I would, maybe you had some additional input and so on, but at the end I'm sure you had this conclusion, then I can promote this conclusion to be my own conclusion. So in other words, if I'm certain that John is certain that there is a dessert tonight, then I'm also certain that this will be served. That's a rule that you assume for the moment. It's an assumption, as I said. It's not something that follows logically, but it makes sense. It's kind of capturing the fact that we are applying the same rules and that they are consistent. So let me write that down. So if agent A, this would now be me in this example, is certain that agent A prime wrote into his, now it's his notebook, that, let's say here, wrote in this notebook the following: I is now this A prime. I'm certain that, let me again use this blah, set equal blah. This is a particular outcome. Then A can also write into, let's say it's her for the notebook, I'm certain that set equal blah. Actually would be in serious trouble if this was not the case, because this is essentially what we do whenever we communicate. So whenever you tell me like when I learn something, I mean essentially all my knowledge that I have, except the few things I've seen myself, but all the knowledge I have about the world is kind of indirect knowledge that I knew that someone knows that, and I promote that to my own knowledge. I don't, of course there are people I don't trust, but this is not about trust. So here the agent has, all these agents have been programmed by the same physicists, let's say, with the same rules. So they should by definition trust each other. So that's another assumption. But clearly these are rules. These are just now rules I program into the computer. And we can later come back to the question whether these are good rules or not. At the moment it should just be clear what the rules are. Okay, now we are prepared for the actual thought experiment. You see, there is now no consciousness appearing in this thing, and you will not need to know more about agents. Agents are really just computers that follow these two rules. That's all. Yes?
I don't get the point why you impose the state to be a basis.
Aha, I just impose. Okay, probably it's not so clear why I do that. It's just a weaker assumption if I do that. I want to state as, you see, at the end, what will happen, I will do something similar to Wigner's argument. I will at the end show that the assumptions we are making are contradictory. So the weaker the assumptions are, the stronger is at the end my argument. So here I'm saying, I don't even need to know what quantum theory tells me if you have not a deterministic case. Maybe clearly quantum theory tells us something about that case, but I don't even need that. And indeed, if I had, I could also include, say that if this is not 1, then the agent writes into his notebook that I'm 50% or 70% certain that this will happen. I could do that. I just don't need it for the argument. So in some way, I'm not saying nothing can be said if this is not 1. I just don't need it. I need kind of a restricted quantum agent who only knows how to deal.
So the agent knows the state of the system.
We will, yes. So this is what I should maybe stress that again. Or I didn't say it very explicitly. So I will now, in this thought experiment, which I'm now going to describe, assume that all agents are programmed in such a way that they know the entire experimental setup. They don't only know their parts. They know everything, like the whole setup. They, however, so the different agents have access to different outcomes at the end. So the distinction between the agents is that maybe one agent sees this outcome, the other sees that outcome. But the entire setup, what you will now see, is the same as all the agents. So they know the overall state, they know the initial state, they can know which unitaries are applied, they know everything, and they apply these rules. So in addition to these two rules, I also program into the agents a description of the thought experiment. That's what I would do. And that's then all what I do. So I program them to follow the rules, plus I program into them what I'm now going to describe, which is the following experiment. Okay, now we don't need, for the moment, Wigner. Maybe I'll erase that because it's good to have this middle blackboard here, because I will actually need 2 blackboards in a row. So what I'm building up these thought experiments in essentially 3 steps. The first step is something that you already are very familiar with. So one ingredient to the thought experiment is essentially Wigner's original thought experiment. So what I'm going to do is the following. I will draw here a huge line which is supposed to be a time axis. So here is t. And I will have certain specific points on this time axis. And let's say I start with at certain time 0. Then let's say something happens at time 1, or something starts at time 1. Then maybe, okay, because it's really a kind of longish experiment, I will maybe continue here. Let's say I do it like that. I think this picture will not be needed. So the time axis continues here. I think it's okay if I erase Q, because we all know what quantum theory is. This is not something special. Okay, so the time axis continues here. So there's again t. Here is let's say here is time 2, then here is time 3, and here is time 4. So it stops at 4. You can think of these as minutes or seconds or whatever you like. Now, so this is of course schematic thing. So if I draw here a lab, this doesn't mean that the lab only exists at time 1. What it's supposed to mean is that something non-trivial happens in this lab between time 1 and time 2. This is the way you should read this picture. So what happens in this lab? What happens in this lab is exactly what happens in Wigner's thought experiment. So there's a person within the lab whom I call F, as in Wigner's thought experiment. And as in Wigner's thought experiment, this person has a measurement device. I will now use a slightly different thing. So I will say this measurement device outputs the vertical direction of a spin. So it measures a spin in the up-down basis. Maybe I write here into the device the measurement basis, which is just spin up and spin down. So this is really the same as we considered yesterday. The only exception is that I assume that the spin is injected from the outside. So there is one moment in which the lab is not isolated. There's, so to speak, 1 qubit of communication into the lab, but otherwise this lab shall be perfectly isolated until it's maybe measured later. So this is lab L. I use the same notation as yesterday. I inject at some point a spin particle in a state phi s at point 1. And the measurement should start at 1, and it's completed before time 2. That's the assumption that I make. So the person has some time to carry out the measurement, and this person is now an agent, so given the measurement outcome, she will also, so she has a little notebook here, will write conclusions about what she can say about other things of the experiment. She will write that onto her notebook according to the rules. So that's essentially the starting point. Now, there will be another measurement being carried out, which I draw here at time 3. So I guess this is clear, but please ask if not. This is really just the same as yesterday. So this whole lab, so maybe I draw this arrow. So here is the lab L. So the whole thing continues from the left, but nothing happens between time 2 and 3 to the lab. There will be other things happening, but not to the lab. So at time 3, there is an outside measurement applied to the lab. Like the measurement that I considered yesterday that Wigner carried out. And this is indeed, I think, here of a person, another agent, Wigner, who carries out the measurement. And he's really a very powerful person in the sense that he can apply an arbitrary measurement to an entire lab. This is why it's a thought experiment and not yet an experiment. But if you think of this as being a computer and not a human, then it's not a completely unrealistic experiment. So it's something we could actually, at least in principle, carry out, because we know how to model computers, and we only need to do the measurement on the logical degrees of freedom of the computer. Now, to describe the basis of this measurement, I need to introduce something. So maybe you remember yesterday what I said is that if this system here, so what is the state of this lab L at time 2? I can just define that. So let me do the following. So if I have if phi s, so maybe write this like that, if phi s is spin up, so this is one particular case that I could consider, then there is an evolution, time evolution from time 1 to 2. So this is the time evolution during the measurement. How does the lab evolve? Now the only thing I'm assuming, and this is now part of this assumption that we have quantum theory, is that because the lab is an isolated system, it evolves unitarily. That's my only assumption here at this point. So there will be some new state. So this is the state of the spin. And the lab is now in some state, which I could call plus 1/2. This is the whole state of the lab. So yesterday I wrote, maybe you remember yesterday I wrote this as the spin is still up in S, the device shows plus 1/2, and the friend F sees 1/2. So this is what I wrote yesterday. Maybe I put this into brackets because we don't, this is a specific way how you could think of that state plus 1/2. But the only thing I need here is whatever this evolution is, and this friend may write things on the notebook, at the end of, at time 2, the state will be still pure, and I call this pure state plus 1/2. It's kind of a definition of this state plus 1/2. Now I could also consider the opposite case, namely where if the spin is spin down, and I again have the same time evolution, then there will be another state, and this state I call minus 1/2 of L. And obviously because these two states are orthogonal and because the evolution is unitary, these two states will be orthogonal. I will not need anything to know anything else about these states. So we just know at the end of this thing, this lab will be either in that state or in that state, depending on whether the input was that or that. And of course, if it's a superposition of the two, the outcome will be a superposition of these two states. That's what we have discussed yesterday. So now let me define the measurement basis here. And okay, for that, maybe I'll erase this because I think this is also pretty clear, this assumption C. So what I'm now doing is I define a measurement basis in which H and W applies her measurement. And this is exactly the measurement basis we already discussed yesterday, but I will give it a name. I will give the name, and this will become clear in a minute why I call it OK. So because we will actually run this experiment until we get that outcome. So I can define a state which I call OK, which is defined as just the superposition of the state which I called plus 1/2 of the lab minus, this is important, there's a minus sign, the state which I called minus 1/2 of the lab. And I will define another state which is orthogonal to that, and I will call it fail, it's the opposite of OK, which has a plus sign in between. Now the idea is that this measurement is exactly in this OK fail basis. So the measurement that is carried out here is with respect to the basis OK fail of the lab. And there will be an outcome which is either OK or fail. Yes?
Are we assuming that F and D have a ready state also?
Pardon?
F and Z have a ready state?
Aha, yes, so here, yes, right. So if I say here time evolution, of course the rest, yes, that's right. So the rest of the lab here, I only described here the spin, is in some ready state, right.
But in that sense, that thing is not complete.
Which thing is not complete?
The measurement is
Aha, yes, so this is not so indeed, so this measurement, maybe you should think of a potential, so of course this lab could have be a very high dimensional system. just think of them as two states of a huge basis state. But it will turn out that we will only be in that subspace. So we will remain there. So indeed you could write other states here. That's right. Thanks for the remark, because that's sometimes unclear when one talks about these high dimensional systems. Okay, now let me make a remark. What is okay, maybe I write it here. The remark: if phi s is now a superposition, and let me use a convention. The convention is that I used this convention already yesterday. I write spin right if I mean spin up. If I mean spin up plus spin down. So now let me ask you a question. If phi s was prepared as spin right, what can we say about the measurement outcome W that we will obtain in this measurement here? So what will be this outcome? It will be fail, yes. So why is it fail? Here we have a superposition of up and down, so we have a superposition of +1 and -1 with a plus in between, and the state fail here was defined with a plus in between. So indeed we will get fail. So this was just to check. I hope this is clear to everyone. Please ask if not, because we will use that later. But this was essentially what we said yesterday, that this is a way to test Wigner's thought experiment. And indeed, what Wigner would have said is that Wigner would have been successful if he sometimes here got an okay, because he would say it's not true that there is unitary evolution, so the state will actually not be a superposition but a mixture. And if it was a mixture, then this prediction that it will always give fail would no longer be true. So according to Wigner, we would sometimes get here an outcome okay. But now we are assuming quantum theory is universally valid. So in this case, we know under this assumption W will be fail. And I asked you yesterday who believes that, and everyone said yes. We would think this is, if we actually did the experiment, this will happen. And I think that's the common understanding. I think there are few people who doubt that. Okay, so now we can start with the more interesting part. So far, it's essentially just Wigner's initial experiment with this addition that we measured that. And by the way, the idea of measuring that has been discussed intensively, and I think even proposed by David Deutsch, who said that this is actually a way to make this argument experimentally testable. Now I go on and introduce an additional element into this picture. And this is the key additional thing that we'll need, namely that you notice I have here injected the spin, and this gives me the freedom to choose this spin in some way differently or randomly, if you like. So what am I going to do? I'm now thinking of another lab here. And the action in this lab takes place between time 0 and time 1. That's why I draw it here. So this is another lab, and the spin will be prepared within this lab. So this lab is also perfectly isolated, except for one little moment before time 1 where the person in the lab is allowed to send out the spin particle. So there's one qubit of communication between this lab and this lab, and I call this lab L bar. And there's also someone in this lab, and maybe it's not a surprise that I call this person F bar. So everything is bar here. So what does this person do? This person does the following, or this agent. Maybe I should really stick with the name agent, because it could be a computer again. So what does it do? Suppose this, in the lab there is also a random number generator R, which generates a random bit R. And I will call this random bit to stress the point that it's a random number, heads or tails. So it's a random coin. It can be one of these two outcomes. So it's kind of a coin flip. But I will, to be clear what it really is, let's also suppose this is a quantum system that generates that. So you can think of this as a kind of a system that is prepared in a superposition of heads and tails and then measured in the heads-tail basis. This is a way to implement this is the way we actually generate random numbers using quantum devices. You can even buy such devices. So this is at least a part of the experiment that really exists technologically. Now, for technical reasons for the argument, I will need that it's a biased coin. So tails should appear twice as often as heads. So maybe I write this is in the relation is 1 to 2. I will need that later. But for the moment, this is not important. This will become important later. Now, what should f do? F bar has now a rule to follow. And it's a computer, so we can program into it this rule. It should do the following. If R is heads, then prepare phi s equal spin down. And if R is tails or else, I mean these are the other only two options, prepare phi s as spin right. So only in the case where we have tails we do kind of the original Wigner's friend argument. In the other case we just prepare spin down. That's fine. And of course if we prepare spin down it's clear that this guy here will get the outcome. Z direction is -1/2 if you like. I hope this is also clear. Please ask if not. Because now we are starting with asking ourselves, what do these agents write on their notebook? So I assume this agent also has a notebook here. So this is already the second stage. I told you I will make 3 steps in describing these experiments. This is the second. There will still be something coming here between time 2 and 3, but what comes here between time 2 and 3 will not affect the lab L. So there will be something, some measurement, maybe I write that already here so that there's some space free. So there will be a measurement applied to the lab L bar at between time 2 and 3. And I will describe that later. That will also give an outcome W bar, and there will be a person W bar who observes that outcome. And I will, okay, but that's for later. Now, let's start asking what do these agents write on their notebook. So whatever we do from now on, I will just only ask what will be written on the different notebooks. I will do nothing else, essentially. Now maybe I can continue here. I have here some notebooks. So let's maybe start with agent F bar. And I will only be interested in what he writes on his notebook if he gets tails. So let's say if the outcome of the random number generator is tails, then F bar writes, and maybe I write the time. So if R is tails at time, this is at time 1. So at time 1, this what he did is kind of completed. So at this point, it's certainly well defined what the outcome is. Then F bar writes the following into her notebook. I is now F bar, certain that W, and now I do, at time 4. So he will, based on the fact that he has tails and he knows what he prepares, I mean he prepares now spin right, he makes a prediction or a statement about what will be the outcome, what he thinks will be the outcome here, W measured by the agent W. And what should he write here? So if we now apply the rules of quantum mechanics, what should he write into his notebook? Any idea? Fail, yes. Why? Just because of the remark we just made before. I said if phi s is spin right, which is of course the case whenever R is tails, he prepares, by definition of the experiment, he prepares spin right, and we have already seen that if spin right is prepared, W, the outcome will be fail. So there's nothing, this is really now what I mean by applying quantum theory. This is now the example of, the computer could calculate that. The computer has programmed everything, and now the computer sees R is tails. Now I can write on my notebook that W will be fail at time 4. That's how it works. So this is a process that a computer can carry out. Now let me do something else. Let me now consider agent F And let's suppose he got outcome plus 1/2. Then what can she write into her notebook? So I'm claiming she can write something about R. That R equal at, so this is of course at time 1. So and Z plus 1/2, this is something that is available at time 2. Time 1, this is at time 2. So what should I write here? This is now a question to you. Pardon? I didn't. Tails. Someone said, who said it? I didn't. Oh, yes, you said tails. Who agrees that you should write tails?
She cannot be certain.
She cannot be certain. Why not?
Because you can get same outcome for both of states, even if it's up or even if it's right.
So maybe you can think of it as follows. So if R is tails, then the spin is a superposition between up and down. So F could get up or down. If the R value was heads, she would certainly get minus 1/2. So clearly if she sees plus 1/2, she's sure it cannot have been heads, so it was tails. Is that clear? Who doubts that conclusion? Just to make sure, because here we need to be on. So no one doubts that. So indeed, that's what, I mean, this is actually an experiment we could really do, because so far we didn't use the fact that these labs are isolated to make that conclusion. We could go there and see whenever this person F gets plus 1/2 and we check what was the value R, we will actually find that it's tails. So this is clearly undisputed. And of course an experiment would confirm that, there's no doubt about that. Now comes the interesting part, which now uses this reasoning about others who use quantum theory. So far I didn't use that. So, but okay, there's a first step which is just in some way pure logic. It doesn't even involve any assumption. So if F Z is plus 1/2, then F can also write the following. Maybe I say here, also writes the following. What can she write? She can write, I'm certain that F bar wrote into her notebook. What can that? So what can she write here? So I mean, you now can see she's already certain that R is tails. Yes, right. So exactly. So F bar is certain. F is certain that R is tails, and we have already seen that if R is tails, then F bar writes that W is fail. So therefore, F is now certain that F bar wrote into her notebook that W will be fail at time 4. This is just a statement about her notebook. So notice this is not a statement about what W will be. It's only a statement about what she would find if she went there and read the notebook. And it's again something we could just verify in quantum mechanics. I mean, that's up to this point there was no, up to time 2, there is no complicated measurement being carried out. You could just do that. Someone writes into a notebook a conclusion and the other party checks whether the conclusion is right or not. So, by the way, what assumptions have I used, or what rules have I used so far? To derive these two statements, I've just used the rule Q here as well. That was, I used quantum theory. Here it was just logical combination of these two. I didn't use an additional rule, but now I'm going to use rule C. And of course this is also just a rule. So this is what the computer would do. It would now conclude that if Z, again this is only true if Z is plus 1/2, then F also writes. What can she now write if you apply rule C? Does anyone remember what C said? So we have such a statement. She's certain that F bar wrote into her notebook that this holds. Right. Now, this was the example I made with John as a victim, so to speak. If I'm certain that John wrote something, then I can be certain that this is true if we agreed beforehand that we apply the same rules. I mean that. So she can now write, I'm certain that W equal to fail at time 4. Okay, now we have some notebook. So now we have just made statement about notebook's entry, which we will at the end of the experiment verify in some way. So we can go there and check what is in. Okay, I will maybe later comment on what we can directly verify and what not, but that's because that's kind of a subtle issue a bit. Now I make a yes. There's a question.
So for that second statement, why is from the rule Q? Because I think that rule says your agent can say she's certain about something only if that's the state phi has overlaps with a certain measure basement with probability 1.
Mm-hmm.
In this case, like if the R is tail,
Here you mean this statement? You are okay. Yeah, so this is indeed a statement that I can derive from having overlap 1 or okay. I mean overlap 1 and 0. Okay, I mean I wrote here when I wrote it. I wrote the overlap 1 will certainly occur. That's equivalent to say that an outcome with overlap 0 will never occur. And now this makes it easier to think. This is of course equivalent because if one vector has overlap 1, then the other vectors all have overlap 0.
I mean, because
No.
if F bar prepare the state as that, so the situation of
Yes,
the mind.
I know what you mean. So actually the argument is via this thing here. So what you use is not what happens if you have that state, but you use what happens if you have prepared that state. So if you prepare that state, then you're sure the outcome will be -1/2. This is a certain prediction. So you could say the certain prediction is kind of, maybe I write it briefly here. If R equal heads, then, now this is really the rule with overlap 1. If R is heads, I have that, then Z is equal to -1/2. So I guess you agree that this is a conclusion that can be derived from just knowing what happens with overlap 1 statements. But now, this is logically equivalent to say that if this is not -1/2, which means it's actually maybe which is +1/2, then R is not heads, which means R is tails. So I actually should make 2 steps and say I derive this statement.
So I think I understand this part. What I'm saying is in rule Q, it seems the agent already knows how that state phi is prepared. So based on this rule Q, she doesn't make any more measurements. He just knows that this state overlaps with some of his measurement bases, and he write down whether she's certain about some outcome. So now if this agent F knows how the state is prepared, so she knows it's in this state point to the right. But now this state does not overlap with any of his measurements.
Yes, that's true. It doesn't overlap with up or down, but this is not needed for the argument. So you never need to know. So what this state is irrelevant to get this conclusion here. So that's my point. So actually I could have here any state and I can derive this. So I simply don't need it because, again, what I'm doing is, suppose R is heads. In this case there is overlap 1. So I get to that statement. And now I just write the logical equivalent of that statement, which is that statement, which is the statement I'm looking for. And in this argument I never used any, in this argument the overlap between this state and the +1/2 and -1/2 never enters. So I don't use that overlap. Or where did you think I used it? Maybe I...
So I'm just saying that it seems you are using more things than just the rule Q. So in rule Q, because you are certain that state overlaps with 100% probability
Yes.
with your measurement basis. So after that, you didn't change the original state. But now, I think after this measurement process, you are changing the original state.
No, I'm never talking about the state after the measurement in this rule. Of course, the state after the measurement is somehow maybe defined, but I don't talk about what is the state of the spin or so after the measurement. So, you see, the only thing I need, so you see, the crucial thing is to derive this thing. If R is heads, what is Z minus 1/2? The only thing I need to know to arrive at this statement is that if R is heads, by definition the state is prepared like spin down. The other thing I need to know is that the measurement that this person does is with respect to the basis down up. So clearly if I've prepared a spin down state and I measure it with the spin down up basis, with certainty I will get spin down. That's the only thing I used. I didn't use anything else. I post measurement or changed a new state after the measurement. I only used that. So essentially, in other words, if you prepare a state down and you give it to me and I measure it in the up-down basis, I will with certainty measure spin down. That's the only thing I used in the argument. That's this thing. And this is just logically equivalent. Maybe I didn't fully answer it, but maybe we can discuss it later, or maybe someone has a not better explanation. Or, yes?
Not an explanation.
Yes?
So we are assuming that if you measure some outcome, the state has been projected to the corresponding.
No. Actually, I'm making an assumption about the state after the measurement. You see,
How do you know you can prepare? How does F bar know that they can prepare those states?
Aha. Okay. That so assume that if I describe something in the protocol, we can do it. So, of course, you could argue what I write here, prepare a spin down, is not possible. You can't just not prepare a spin down. But of course, we know how to do it in the lab. So I assumed implicitly that the protocol I write down is a feasible protocol. So assume that if I tell you go into the lab and prepare a spin down, you will be able to prepare a spin down.
I think measure in the Z bases and discard ones where I get spin up.
Now I see. This would be one possible way to prepare a spin down state. Of course, spin down, you see, this is kind of abstract. You could think of it as any two-level system. You could do the experiment with, let's say, ions which are excited or not excited. And if I tell you prepare an ion in state 0, in the not excited one, you may have some method to make sure it's not excited. This method may involve some measurements, but maybe not. Usually they do indeed, but so I don't here talk about how exactly you prepare a state. I just assume you can do it. Now, of course, it's allowed that the state preparation itself consists of doing some measurements and conditioning on these outcomes. That's fine. That's like when I do quantum computation, we sometimes say, let's start with a 0 state. I don't talk about how you prepare it, but assume you can somehow prepare it. Yes?
Is it the case that this L and L prime are two closed systems, but the friend in L knows the basis of L prime?
So yes, that's also important. So I assume all the agents know the entire setup. So the agents know essentially what you know now. They would see this whole description. At the end, they're put into one lab, but they know what's going on. They don't see the outcome. So this person here doesn't, of course, see the outcome set, but she knows how F measures.
Is it a closed system?
It's an isolated system. Yes. By definition. We have to distinguish questions about how easy it is to actually implement it or not. But in the thought experiment, by definition, it's one. You may now argue for some reason that we will never be able to create a big isolated system. That's fine, but that's then part of the universality of quantum theory, if you like.
Because they share some information.
Yes, so that's why I stressed here, the system is isolated up to 1 qubit of communication.
Okay.
So they can really send this spin from here to here, but otherwise they are isolated. So this is well defined. I can say they're isolated, but at some point it's allowed to send one spin out. Okay, now comes the last step of this thing. I said there is something here. And to define what's going on here, let me make an additional, or let's maybe for the moment see what's happening in the lab, in the upstairs lab. Maybe I write that here somewhere. So I can do something similar to what I said for the lab L. So in L bar, let's suppose that if this random number generator was such that it was actually not prepared to generate random number, but just it would always output heads. I mean, you can think of the situation. We replace the random number generator by one which always outputs heads. Then there's a time evolution again. Evolution between from time 0 to 1. And what will be the state at the end of the lab L? The state will be some state which I just call heads. So in some way this is the state of the lab L if the person in the lab has seen heads. And of course in this case also she prepared the spin as the spin downwards. So that's what's going on in the lab. And then of course this S is sent away. And the same thing is that if the initial random number generator was tails, and there's again the time evolution, then I can by definition say the lab is now in a certain other state, which I call tails. This is just the state it would be in if I started like that, and in this case the spin is prepared as spin right. Okay, now I hope this is clear. This is just a definition of state. So the lab will be in some state, and I call that state heads and that tails. And now I can again make a definition of states as before. I call the state OK bar of the lab L bar is the state where I have the heads state of L bar minus the tails state of L bar, and the corresponding fail state. This is just a definition. So this is a possible state on the whole lab, and I'm allowed to make such a definition. Of course, it's just a definition of a state. This is with a plus, so this is orthogonal to the other one. And now the reason why I introduced this definition of OK bar and tail bar is that I will assume that here in this measurement you will measure with respect to that basis. So I assume here there is a measurement with respect to the basis OK bar, L bar, and fail bar, L bar. Okay, that we can do. I mean, this is a particular, again, I mean, your comment applies. There is, of course, this is a higher dimensional space, but we will certainly be in the subspace spanned by OK and fail because we just defined these states in that way. Yes?
Is the random number generator inside L bar or is this outside L bar?
That's a good question. So the random number generator here should be inside the lab L bar. Yes.
So is it a quantum system?
Yes. So I assume. So I assumed. Maybe I write this briefly here. I have still some blackboard free. So I actually assume the random number generator is a random number. R is generated in the following way. I said heads should be only half as often as tails, so I could prepare a state in this space. I could prepare such a state where heads and tails are just two orthogonal states of something which I could call a coin. See, and I measure this in the I measure this in the heads-tail basis, and I get the value R. So this is a quantum system, and assume this quantum system is part of the lab L bar. Okay, now because of time and because anyway, I think I was asked at some point to give some little exercise. I will now skip a small part of the calculation. I can do it tomorrow if you like, but I want to arrive at the conclusion. So I skip one part, and you just have for the moment to believe me, and then hopefully you can actually verify it until tomorrow. So it's just a claim, which is the following. Claim that maybe I write it here because I need a bit more space to make that claim. So the claim is about what can now H and W bar say. Again, when W bar applies quantum theory. And this is something you can really now verify from what I've told you. This is a quite straightforward calculation. It's maybe 3 lines. So this is again a conclusion I can draw from Q. So Q is this rule. And now is the following. If W bar is OK bar. So if he got this outcome corresponding to that state OK bar, which I defined there, which is an overlap between heads and tails, then, so this is at time 3, then W bar writes into her notebook the following: I am certain that Z is equal to plus 1/2. So this is something I just claimed, but this is a straightforward calculation, and I ask you to verify that until tomorrow, and we can discuss it tomorrow. So it's you need to write down the state of the whole system from the outside, but it's pretty unambiguous. You cannot go wrong. You just need to put the signs right and so on. Now, of course, I can again do the same steps as before. So if W is OK again, so under the same condition, then W bar can also write, do the same really as before. Now, because she knows that Z is plus 1/2, and now notice we have here on the left-hand side already said that if Z is plus 1/2, then we know what F writes into her notebook. So we can just therefore say that W knows that he is certain. So he writes, I'm certain that F wrote that she is certain that W is fail at time 4. And now, of course, you now probably can guess where this goes. So I can again apply the rule C, the consistency between the different agents, which says now that she can promote that to her own knowledge. So W also writes, she can now be certain that this is really the right conclusion. So she can now write, I'm certain that W is fail at time 4. Now there's a last step I would like to do, and then we are essentially done. Suppose that agent W bar, he's not in an isolated lab. So he's a lucky guy, he's outside as well as W. Suppose he tells W what he just gives him his notebook entry, so to speak, or tells him what he wrote. So we can therefore say that at some point, again, so strictly speaking, you again use C, because if someone tells me what he wrote into his notebook, then a priori I'm only certain that he wrote that into his notebook. And then I need again to use the step C to say, oh, actually what he wrote in his notebook is something I can also take as a truth. So we can say that W, he's the other agent. If he has heard from the other guy that W bar is OK, writes also into his notebook. Okay, that's now kind of a trivial step. Of course, if your colleague writes that into a notebook and tells you that, then you can also write that into your notebook if you trust him. Again, it's an application of the rule C, that I'm certain that W will be OK at time 4. But notice he can write this into his notebook at time 3 already. Because at time 3, or maybe shortly before, maybe I say that before time 4. Before. So he can kind of make a prediction about, so W has now written something into her notebook. He has written that at time 4 I will see that the outcome W is fail. Sorry, this was wrong. here I should of course write fail, because we always had fail. Okay, so what's the conclusion so far? We know that if we run this experiment, and let's suppose we are now W. So take the position you are W. Now your friend W bar tells you the outcome that he has seen was OK bar. So we are essentially in the situation as we are now in this audience, and we know that. So what we know is written here. We see this whole setup, and we know W bar was OK bar. So we wrote into our notebook here. So this is the notebook that W has. We can write, we are certain that W is OK. Is fail. Sorry, I can make this mistake. W is fail. That's what's the conclusion. That's what we would now write into our own notebook. Now the point is the following. This is again something you should verify, and I will again come back to that tomorrow. We can also now calculate what is the probability that W bar is OK and W is OK. This is again an exercise maybe for tomorrow, so let me put that here. So by the way, I should maybe say this was also one exercise, maybe that, let's call that exercise 1, and I will come back to that tomorrow. Now the exercise 2 is the following. Prove that, or it should be, you should do it, so prove that the probability that W is equal to OK bar and W is equal to OK is actually 1 over 12. Okay, this number is not so important, but importantly it's positive. So what does that mean? If we really run this experiment, there will, after just a few cases, maybe we run it 20 times or 100 times if you like, at least at some point we will have a situation where this guy will report W is OK bar, and this outcome will also be OK. So W will also be OK. So we'll have the situation here, W is OK. And now you see we have a problem, because, okay, what this guy wrote into his notebook was, I am certain that W is fail. So that's what we concluded before. He said he writes that into his notebook. So we are in a situation that in some of the when we run this experiment and we wait until both of these things are okay, we can go there and look on the, if you think this is again a computer, look on the computer's output notebook, what was his prediction, and we will find that this prediction contradicts the outcome we have actually seen. So that's, let's say, the bottom line of today's lecture, that we have now constructed an example where we have just programmed computers with quantum theory together with this rule. So we had these two rules, Q and C. We have programmed our computers with the rules Q and C, and it turns out that if we run these computers, at the end of the day we will find on the tape or on the notebook that these computers produced that they are certain about something which is, however, just the opposite of what actually happened. Which proves that these were not good rules, obviously. So at the beginning I tried to tell you these are very natural rules, but that's the point of this thing. So this argument shows you that something is wrong with these two rules. And now you can see whatever interpretation you have, and we will discuss that tomorrow in more detail, whatever interpretation of quantum theory you have, you better make sure it violates one of these rules. Otherwise, you are in trouble with this thought experiment. So any interpretation of quantum theory which says you can't just use quantum theory universally, and at the same time you are consistent with what other agents say. And this is actually true for most interpretations. Certainly all hidden variable interpretations. They declare that, of course, we agree on, so, I mean, if there's a hidden variable telling you what the outcome is, then clearly, if I'm certain that someone else is certain that this has a certain value, then it is that value, because there's just this variable. So what I'm telling you is that it's very hard actually to find an interpretation of quantum theory which does not satisfy both of these rules and still make sense. But if it satisfies these two rules, it's necessarily a bad interpretation, because it leads to, if you program a computer according to your interpretation, the computer will produce a wrong prediction. So this is at the end a verifiable thing. So the computer runs and will produce this prediction. So I hope this was more or less clear. Let me just, because this is an important conclusion, just summarize it very briefly. So what we did is we took agents to be essentially computers that we can program according to rules that we think are good rules, that they capture physics well. And so if you believe in quantum theory, one of the rules is the rule that we called Q, which is essentially, you could say, the Born rule. And now it's important, we just looked at one special case of the Born rule, namely when it gives a deterministic prediction. We didn't even bother to program the computer about what happens when the prediction is non-deterministic. We just look at the very simple case where the prediction is deterministic, where it's apparently almost classical in some sense. And then we also programmed another rule which says, in some way, captures the fact that an agent should consistently be able to describe another agent, in the sense that if he finds that the other agent finds a certain result, then he should believe that this is now also a result that is valid for him. Also, again, only in the deterministic case. So it's not about assigning a result to something which is counterfactual, because I'm not sure. So I'm already certain this guy wrote that into a notebook, and it's experimentally verifiable. So at any point you could stop the experiment and go there and check, is the notebook entry that thing? And it would be that according to quantum theory. So you assume that as well. And if you program, now we found in this very special situation, which admittedly is very unnatural, but it's a possible situation, we find that these rules are not good rules. They lead to a wrong prediction. Wrong in the sense that at the end of the day, the computer's output will not match the actual outcome. And so this now will lead us back tomorrow to the discussion of interpretations of quantum theory. We'll go through the interpretations of quantum theory, and it's interesting that they will locate the problem at different places. So some interpretations will just say one of the predictions that one of the agents derived was just wrong according to that interpretation. And some other interpretations, they, for example, kind of try to deny that there should be this consistency, but that's a bit harder then to capture. So we will use tomorrow this example to discuss different interpretations, and I hope that at the end of tomorrow you will see what the problems are with the interpretations and what possible directions could be to find an actual interpretation which avoids all of these problems. Some people asked me yesterday what interpretation I prefer. So because in my opinion, all interpretations that I'm aware of today somehow run into this problem of satisfying these two. They're all, in my opinion, not yet satisfactory interpretations. That's just to say what. So I will not favor one, and this would anyway not be the goal of this lecture, to kind of convince you of some interpretation. If you want to convince you of anything, then it's only the fact that it is interesting to think about interpretation, because it's a non-trivial and I think very important problem to find a view on quantum theory which avoids the problem that arises if we accept these two rules. Okay, that's all for today. And please, I encourage you to look into these exercises. They will, because if you can solve them, this means you can it is confirmation you have understood the thought experiment. If not, there was maybe something I didn't explain properly, and I will come back to that tomorrow. Okay, thanks for your attention. Okay, there was a question here. Maybe I can still, if yes.
Just to go back, you're assuming both the labs L bar and L are totally quantum?
So whether they are totally quantum?
Because
yes.
I guess that was the assumption.
So yes, so the assumption of the universal use of quantum theory is indeed that these labs, L and L bar, are treated as quantum systems.
But then you used, on the random number generator, you used Born-like measurement to find the...
Okay, maybe this was just an intuition. Okay, that's a good point. I said I defined this. I don't know where I wrote it actually. I don't find it then. Probably it was somewhere here behind or so. So I wrote somewhere where this random number generator has 1/3 heads plus 2/3 tails. And I said this will correspond to having with probability 1/3 head. So you should better I should maybe have said just define the random number generator to be a system which is initially in this superposition, and you don't need to bother that it means that it's with probability 1/3 heads or tails. I don't need that. I just take it as a system which you prepare in this particular superposition state and measure it. And in the argument actually when you do the calculation, you will never use the fact that heads appears with probability 1/3. What you will use is that there is this amplitude of square root of 1/3, but you will never have to apply the Born rule to the quantum random number generator. So in this sense, this was more an intuition where I said it's giving with probability 1/3 this outcome and 2/3 that, because that would be our understanding, our interpretation of it. But it's not important for the argument. Important for the argument is only that it's a superposition of heads and tails that you measure in the heads-tail basis.
So what you will be actually preparing is a superposition of the down state and the...
Yes. So when you do this calculation that I ask you to do in exercise 1, what you should do is really to write down the overall state of the two labs, which will be a big entangled state. And from that state you can draw the conclusions. Yes?
So if W hears something, how can the system he measures or she measures be isolated?
So, yes, so maybe I wasn't very, so when I said these systems are isolated up to the point where they are measured. So I keep them isolated, and of course, in order to apply the measurement, the measurement will be a very highly or decohering process for the system. So indeed, what I meant here is, for example, here this system remains isolated up to time 3, and now you apply a measurement, and of course, to do the measurement, you break the isolation and so on.
Sure, but then nobody can hear or can talk about what's going to come
Yes.
before doing the actual measurement.
Right. Yes.
So
That's.
there can be a contradiction between writing down what will happen and
Uh-huh.
what will actually happen.
No, actually, the communication, there is no, you see, in some way the communication, for example, is via the spin S. So all we derived here was actually based on things, so there was no assumption that these people talk. So all we derived, all these statements that I wrote down are all based on observation. So for example, W bar, based on his outcome, can infer what set was without talking to the person set. It just knows for certain what set was. So you can see that, talking is somehow the same thing, because what does talking mean? I give you a physical system, a sound wave, and you infer from that I said something. So here it's kind of similar. The person W bar has a physical system which is somehow correlated to F, and the correlation is such that he's certain what F was. This is in some way an abstraction of what happens when we talk, because it's always mediated by some physical system, and they are correlated. That's what allows them to actually make inferences about each other.
All I'm saying is the last thing that you wrote down shouldn't be possible before doing the actual measurement. W shouldn't be able to write down something.
This thing, why not? W is outside. She can write. So you see, at time, so the timing is important. At time 3, W bar has completed her measurement, and of course W bar is not in an isolated lab. She can.
This should be a W bar. Sorry.
This is a W bar,
And the W?
and here is a W.
Because they talk.
Yeah, so W bar talks to W.
But they are not in closed.
So W bar tells W that he has seen W bar. Okay, and now W knows. W bar has seen OK. Okay, I didn't write that they talk, but the idea is that W bar, once he has seen the measurement outcome, announces that to the world, or to W at least.
But doesn't it mean that then the system cannot be in a pure state because it has already interacted with W bar?
After that, it's not. But you see, after time 3, I don't need to look at the state of the system any longer. You see, when you make a calculation, you can see when do you always, so when you do the calculation, always include the times. You see, I was careful always writing the time. So the states of the system changes, and at the end it's maybe no longer defined. So once you have measured an agent, it's maybe very complicated, the state is maybe very complicated and undefined, and I don't need to talk about the state after the measurement. I only need the states at the points in time when they are still well defined. Okay, yes?
So when we write down that part of the statements there, we haven't included that W bar is measuring the...
Yes, that's right, yes.
So I think what we should write is, if nothing else happens, then they are certain that W equal to fail at certain conditions. But now, because W bar is measuring this L bar, they can no longer be certain about the result.
Yeah. Okay, this is a good question. So indeed, I did this calculation before I drew this measurement. Okay, I've drawn already that there will be a measurement, but I haven't told you which one. But this is actually this. Okay. So because we just use quantum theory here, so of course maybe you use a different theory, but if you use quantum theory, then of course, and we only make a prediction about this outcome here, not about something else. So we have a system here, and this system here, the lab L, is not affected by the measurement. It's just a different system.
You can have entanglement between...
Yes, sure, there's entanglement.
When you measure L bar, you can change the result when you measure...
No, there's no secret. Okay, I mean, at least according to quantum theory, let's say I prepare a system. Let's say I prepare this jog in something. Now I put it somewhere, and maybe this system is even correlated to something else. Now I make a prediction about the outcome that happens when I measure this system later, let's say in an hour. But this system is correlated, maybe entangled with something else. Now, the prediction I make about this outcome is not affected by whatever I make with this. Let's say it's correlated to this glass here, because it was actually, I poured water from it. So this glass is now correlated to that. According to quantum theory, if I make a prediction of the outcome here, I just use the density operator of this thing here. This density operator will not change whatever I do with this system here, according to quantum theory.
You're not considering the density matrix, you're considering the conditional probability given some measurement outcome on your L bar system.
No, actually, I'm not. Of course, if I would now condition on the outcome here, then indeed the prediction about that would change. But you see, here I just made a prediction conditioned. So this prediction was conditioned on R equal tails. So I wrote down what the conditioning is. The conditioning is something that was already available before. If I wrote down, so you would be right if I would here write down conditioned on W bar, okay, something would happen. Then indeed that would not be correct, because then of course I need to take into account W bar.
But the final result is like a joint probability distribution for both W bar and the W.
At the end I have a joint, I can calculate the joint probability distribution of W bar and W, that's right.
We need to consider both of these.
Yes, so maybe, okay, this is maybe I would suggest you, because it's a bit hard to talk, I think I derived the individual parts, and maybe you derive it and then you can see where you disagree exactly, because it's a bit hard to discuss that without having the formulas. But the short answer is really that in order to derive that statement, that's just a statement about an outcome conditioned on something which is already available at time 1 and not conditioned on W bar. This statement. Of course, later I have other statements, but to arrive at this statement, I didn't use W bar. But let us discuss that later, because that's a bit technical, and it has to do with these exercises. So if you have done the exercises, we can see how they compare to that.
What is the first exercise?
Sorry?
What is exercise 1?
The exercise 1 is, okay, I had to pose 2 exercises. Exercise 1 is to verify this particular statement, that if W bar is OK bar, so if this guy got OK bar, then he can be certain that the outcome that F got is plus 1/2. This is something I didn't derive, and that's the question. Okay, there was a question here, yes?
So you're not actually measuring the state, you're just predicting what would happen if the state is a certain kind of state and you measure it in a certain way.
Okay, I mean, the question is, what do you mean by actually measuring? So you see, in this whole picture, measuring is kind of a relative process. So clearly, from this perspective, if he measures Z, he would say, I've measured Z and I've seen the outcome. From W's point of view, this is just unitary evolution. So in some way, I would just say one should use the term measurement in such an experiment always relative to an agent. So something can be a measurement relative to that agent, whereas it's not a measurement relative to another agent. Yes?
You decide how to get OK bar and fail bar. Like,
Pardon?
how do you decide OK bar and fail bar?
I'm not sure I understand so what are you referring to exactly?
OK bar and fail bar, like how W bar observe this.
Aha, so these are just definitions, and so these are definitions of basis states. Now the idea is that W bar actually carries out the measurement with respect to these bases. So this is just it's a very complicated measurement basis, but it's a possible measurement basis, and you actually measure. That's the idea. So I guess given the time and the fact that we should have a break, I would suggest that I take further questions tomorrow. I'm very happy to answer all the questions at the beginning or sometime tomorrow during my lecture. But I think we should stop here so that you have a little break before Barbara will start with her lecture. Okay, thank you again.